So in the last video about the Collatz conjecture, we sort of explicitly laid out our pattern for two odd steps that turned into a power of 2, and we found, that it was this 111, 000, 111 that could repeat on. That became 1010 after 3n plus 1, and then this becomes a power of 2 after 3n plus 1. And then we were taking that and we were seeing how it was possible to sort of assemble the components of a binary number in such a way that they behaved, right, in the way we wanted through each of these steps. So this is the first odd step, zeros, and this is a second odd step, zeros. And then, you would have some number made up of these components, and in theory we could go on and maybe there's a third odd step pattern and a fourth and so on. And now there are constraints on this. We can't just chuck in whatever we want and obtain arbitrary behavior of a number. We can't say that we're going to have 2 divisions by 2 after the first odd step, and then 6 divisions by 2 after the second odd step, and then the number will terminate. That particular configuration might be possible, but not all configurations are possible. I'm not really going to get into why. I think the previous video explained some of the details about it, but I don't have a particularly good example right now, and instead what I wanted to do was I wanted to move back to what I'd stated in my introduction video, which is sort of why I thought Alex Kontorowicz's hunch that the Collatz conjecture was false is wrong. And so now that you've got these patterns, you can start to ask yourself, well, I can make some predictions about how a number can behave, right? And so the Collatz conjecture, says that every number that we feed in to the Collatz function, so every number that we give to the Collatz function, eventually turns in to that cycle of 4, 2, 1, right? And so if you take a number that's some binary string of, I don't know, right? What we're saying with this number here, what the conjecture is really saying is that eventually it shrinks, right? So there are 2 other possibilities that you could use to disprove the conjecture, right? Maybe there's some cycle. So it goes from A to B to C and back to A, right? So yeah, I don't know what those numbers are. They're probably huge because we've tested like 2 to the 63 possibilities, but there's some really big numbers that it cycles through. And then the other one is that it grows, right? It grows to infinity, that there's some number, I don't know, m. When you feed it into the Collatz conjecture, it just skyrockets in value eventually, right? It goes off to infinity. And so with these things, you're looking for, to me, you're looking for some sort of stable pattern here, some sort of way that the number could stay stable. And here you're looking for a specific type of instability, right? That the number is adding digits to itself, it's growing. And so if we look at the n/2 step, right, this shrinks the number. And the 3n plus 1 step grows the number. So, right, division, multiplication, pretty easy to see. And so we're asking, does the interplay between these 2 functions, right, these 2 rules that we have that make up our Collatz function together, allow either the number to grow or the number to exist in a cycle? And so let's just look at the lower end of the number with that 10101 pattern, right? So, you know, you know that this pattern, after you multiply by 3, n plus 1, provides a number of zeros that's as long as this, and then we're going to shrink those zeros by n over 2 with that division step. So the minimum zeros that you can generate is 1, right? So the minimum shrink is a single digit, right? So if my number starts with the pattern 1, 1, right? Then I have only 1 0 here, right? And so all my n over 2 step can do is remove a single digit. The maximum shrink, right, is the total length of the number, right, is the total number. So if I have a pattern like 5, you know, or 21, you know, when you're looking at 5 and 21, right, both of these numbers, when you feed them into the Collatz function, immediately turn into all zeros. They sort of collapse catastrophically, right? Like they feed together really well, they slot together like that zipper, and then they collapse down to 1. So you know that, you know, the minimum you can have is 1, and the maximum you can have is the total length of the number. I should say that you can only have odd digits. You can only have odd numbers of digits in these special classes of numbers. You can't have an odd number with an even number of digits that replicates this pattern, right? Because it has to start and end with a 1, because that's how binary numbers work. And then you have to have some alternating set of zeros and ones in there. So you're always going to have an odd number of digits. So I can't construct a 4-digit odd number that behaves in this way, but I can construct any type of odd number with odd digits that will behave in this way. And so, you know, the next question is there, what's the growth, right? We wanted to know what the maximum growth is for a number under the Collatz conjecture. And there are 4 cases. So I'm just going to look at the highest number of digits, the top placing digits for a number. And we're going to look at what can happen, right? So here, this is just sort of some shorthand, but if you recall that binary addition that I do where I'm tripling a number by adding, by doubling a number and adding a 0 to it, and then by adding it back to itself, that 2n plus n is equal to 3n thing, we have 4 cases, right? Like the first digit in our number has to be 1, because that's how a number ends, or the highest digit in our number has to be 1. And then as well, we have a case where we've carried a 1 from some previous addition down below. And then we have the case where we haven't carried a 1 from some previous addition down below. So here, in this one, we have 1, right? And then we carry a 1, and we get 1, 0, 1, right? Here we have a 0, and we carry a 1, and we get 1, 0. Here we simply have, whoops, just made a small mistake there. But here we have, initially our first digit is 0, because we're carrying the 1 over, and then we have 0. And then here we have 1 and 1, right? So these are the 3 cases for our number, right? And so when we look at this, we can see right away that in this case, right, the initial length of the number is the length of the lower portion. So here we only add 1 digit, right? Because the 1 and 1, nothing carries, and so the number doesn't grow. Here, we actually add 2 digits. Here we add 2 digits. And here we add 2 digits as well. And so you can see right away that actually, because the minimum shrink is a single digit, here there is actually no growth in the total number of digits in the number, right? Like the thing stays static, the number stays static. And here there's the growth of only 1 digit. So in the best case scenario for growth, we can only add a single digit to our number, and we also have the possibility that at any moment we could have like a catastrophic scenario appear where, you know, after 1,000 steps of adding a single digit, we truck in to, you know, one of these catastrophic patterns of the 10101, and the whole number collapses. So this sort of fact about the Collatz conjecture is what makes me really skeptical of Alex Kontorowicz's claim that there is a way to find a number that either grows without bound or exists in some sort of cycle. You can actually show that the scenario is a bit worse than what I've just described here. And I'll do that in the next video. But we can sort of immediately see right away that it's very difficult for a number to add digits to itself. You have to have a minimum here, right? Like if you add even 2 digits, right? If you have the pattern 0, 1 at the base of your number, all of a sudden, all 3 of these growth scenarios are static. The number has not added any digits whatsoever. And in this case, it's actually shrunk, right? And if you have a scenario where you have 101 as the bottom 3 digits of your number, all of these shrink, right? And in that case, if the initial number ever becomes less than if the initial number ever becomes less than its initial value through the Collatz conjecture, well then you've got a proof of the Collatz conjecture. I don't know how to show that with this, but it just seems really unlikely to me that you would be able to construct a number that goes on and on or cycles with this type of constraint in it. Yeah, so I guess in the next number I'll show how, or in the next video I'll show how the constraint is actually even tighter than what we saw. So yeah, next time.